Okay, so in this lesson video, we're going to be talking about parametric equations. We're going to introduce you mostly to parametric equations, and then later on we'll go over them more thoroughly and apply them to calculus. But this is a general review, how to graph them, different stuff like that, ellipses, hyperbolas. But anyway, first of all, let's understand how a parametric equation works. So by definition, a parametric equation is a relation, and you have this other variable, the third variable, which is called the parameter, and that is your variable t. And so this variable t is your third variable, and that's what we call the parameter. And it relates to both x and y. So you notice you have two equations, but one's a function of x, like this, and the other one is a function of y. But they're both with respect to that t variable. So in this first example, just to practice, first of all, make sure your graphing calculator is in parametric mode. Okay, and you do that by going to mode, and then it's PAR. Go and put it in parametric mode, and then come back here. And if you go to your y equals menu, you should easily see that you have x sub 1, y sub 1, options, and whenever you hit your variable button, your x, t, theta, n, t will automatically come up. So go ahead and graph that. Answer A as good as you can, because if you go into your window options, you have your t-min, t-max. Just play around with that for a little bit. But for now, your t-min, let's just go from 0 to 3 or whatever you want it to be. Okay? And then your t-step, do 0.1, x-min, x-max, negative 10, positive 10, same with y-min, y-max. So go ahead and graph that and then come back. And when you're graphing it, what you want to do is look for these things called terminal points. Okay, so right here, that's where the graph ends. And we're going to talk about that after you graph it. But look to see if you can tell where the graph ends, or even the initial where the graph begins. Go ahead and graph that and come back. Okay, assuming you've graphed it on your graphing calculator and sketched it, depending on your t-max, t-min, different stuff like that, your graph should have looked familiar. It should have looked something like this. Should touch here though. Comes all the way down, touches 0, 0, and then comes back up. Does that look familiar? Should. It looks familiar because it looks like the parent function y equals x squared. We don't know if it's 2x squared, 3x squared, whatever. We know it didn't move up or down, left or right. Okay, but we don't know if the slope is different than the regular x squared function. Okay? Okay, so we should come back and see, similar to y equals x squared. Sorry, I got sidetracked there. Similar to y equals x squared. Okay, hopefully you got that. Now what I want you to do is go in and play around with, see what happens, because if you set your t-min, let's say your t-min was 0 and your t-max was pi. Okay, if your t-min was 0 and your t-max was pi, then you should only see this red portion of the graph. Alright, and you notice if you go up enough on your y-axis that it actually does have a terminal point. Okay, it does have a terminal point. Now here in this problem, it says make it from negative infinity to infinity, which is fine. If it's from negative infinity to infinity, well, t goes forever negative and forever positive, meaning it says graph forever this way and forever that way. And so here, there is no initial and no terminal point. So no initial or terminal point. So the way they wanted you to graph this problem, there's neither initial or terminal. But if your t-max and t-min are limited, which you can't plug negative infinity, infinity into those values, so in a sense, yes, it is terminated and it does have an initial point. Okay. Now the direction, did you notice the direction that it was graphed? If not, go ahead and graph it again. You'll have to reset everything. So clear out one of them, doesn't matter which one, and then graph it again. And you notice it goes from left to right. So it starts here, so the initials here, and the terminals over here. It graphs this way. So with parametric graphs, it's very important to understand the direction of the curve. All right, so that answers A. Let's go ahead and try to answer B. We already came up with this a little bit, but let's go ahead and find the exact Cartesian equation. And to find the exact Cartesian equation, the easiest way to do this, there's a couple different ways, but look at this. If x is equal to 3t, then t is equal to x over 3. Okay? Now, all we have to do in order to find a Cartesian, remember Cartesian is y equals mx plus b. So in order to find a Cartesian equation, all we have to do is get rid of this t and put it in terms of x. So here we have it. You would have y is equal to 9 times t, which is equivalent to x over 3, quantity squared. So this is x squared over 9. Those 9s will cancel, and so you have just y equals x squared. So the exact Cartesian equation that fits this graph is y equals x squared. Okay, so now this is the basic definition. I've already gone over this, so I'm not going to go over it again, but it's in your notes. Keep it. The one thing that I do want to point out talks about terminal point of the curve, the parametrization of a curve. It's taking, like a graph, a curve, whatever. It's taking a graph and then changing it into an equation that is in parametric. Okay, so be familiar how to do that, to go back and forth. We already did one from parametric to the Cartesian, and we're going to do another one like that. Let's take a look at circles first. The basic, so this is equals. The basic equation for a circle centered at the origin. So this right here is a circle centered at the origin, where A represents your radius. Okay, so just remember to convert back and forth using from parametric, okay, using radius, using radian like this, that your x value is your radius times cosine and your y value is your radius times sine, which basically just gives you the distance it is from in terms of y and then in terms of x from the origin. Okay. And if you remember the circle, it's going to be x minus h. So this is if it's moved away from the origin, hk is your center. So it's going to be then y minus k quantity squared is equal to your radius squared. Okay, so this is the equation of a circle that's not centered at the origin. Let's take a look at this example here. It says a parametrization for the curve is given right here. X equals cosine, y equals sine. So we're going to, part A, we're going to go ahead and graph that. So go ahead and try graphing that on your own, then come back. And if you graphed it, take a look at this. This is very important. Okay, this is your parameter variable, which you have to take into consideration. It says only go from 0 to pi. And remember, it wants to know where it started and where it ended. So in this case, it started here, then it traced up around, and then its terminal point was there. So 0 to pi is the top half of a circle, which makes sense. Think of the unit circle. Okay, so 0 to pi, 0 to 180 degrees is that top half of that circle. Okay, then on B, so this is A, then on B, and direction, so to show the direction, just continue to put arrows in here, and then start and end, you need to label those. Find a Cartesian equation for the curve. This one's simple, since it's, your radius is 1, and it's centered at the origin. It's just going to be x squared plus y squared equals 1 squared, or just 1. Then what portion of the graph of the Cartesian equation is traced by the parametrized curve? We already talked about that. It's the upper half. That's the part that's being traced by this curve. So in your grapher, go ahead and, if you want to, try to figure out what would we have to do to trace all of it. So go from negative pi to pi. See if it graphs all of it. And it should, because it'll go the rest of the way. It'll get this bottom half. So the interesting part is if you go from negative pi to positive pi, where does it start and end? And then versus if you go from 0 to 2 pi, where does it start and end? If you go from negative pi to pi, it'll start here, okay, and then go back around and end at the same spot. Whereas if you go from 0 to 2 pi, it'll start on the right and end on the right. Just interesting. So the starting and ending points are just as important. Now let's take a look at another example, but this time with ellipses. So here's the general equation for an ellipse. There's different ways you can write this. Another way you could write it is x over r sub x. That's the radius of x. Okay, because an ellipse is like an egg. It's a circle that's kind of stretched either vertically or horizontally. So this would be r over, or y over r sub y. That's the radius, quantity squared, and it's always, always, always equal to 1. Never is it ever equal to anything else. If there's ever anything else over here, you have to divide it over. So it's always equal to 1. And so this r sub x and this r sub y, those tell you how far it's stretched on the horizontal axis or the vertical axis. And again, with this x and y, if it's not centered at the origin, you could do something like this. Because that h and k are the center of that ellipse. So it could be moved around just by adding that. Okay, and the parametrization, that's a difficult one. For an ellipse, is x equals a cosine x and y equals b, so in sine t. So you notice that a and b are different because these are the radius, the distance from that center point to the outside, and it's different horizontally than it is vertically. Let's go ahead and do an example here real quick. Go ahead and graph this on your own, see what you do, or see how you do. Remember your parameter, it goes from 0 to pi, and then come back here and see if we get the same thing. So for A, you notice it actually starts here, y equals 2, and then goes around, hits x equals 4, and then comes back and stops there. So there's your initial, and here's your terminal. Goes through 4 like that. Now, if we went from 0 to 2 pi, that would be one complete ellipse, but we only went from 0 to pi. And it was traced in this direction. And then B, find the Cartesian equations for the curve. So use some of those above equations. You should have something like, or something equivalent to, x over 4 quantity squared plus y over 2 quantity squared is equal to 1. There's a couple different ways you could write that. Y squared over 2 squared, x squared over 4 squared, whatever. Okay? Alright, so check your answers and then see if we got the same thing. And the last one, looking at lines and line segments. So this is just as simple as it gets. This is a parameterization for something like y equals mx plus b. So it's just a line. Go ahead and graph this. And then come back and see if we get the same thing or not. So if we graph it, you know, first of all, it's just x equals t, so you can put y is equal to 1 minus x. So it's just a graph of negative x plus 1. So that means it crosses over here and has a slope of negative 1, so it's going to look something like this. Now the parameter, they set it from negative infinity to positive infinity, so that means that it graphs the entire line. Okay, so indicating the direction. Yeah, I believe it. Yeah, it goes this direction, if I remember. It goes that direction. Then it and it graphs the whole thing. There are no initial. There are no terminal. Find the Cartesian equation for the curve that contains. And again, if x equals t, then t equals x. So y is equal to 1 minus x. That's your Cartesian. And the entire thing, if your parameter is set to negative infinity to infinity, so your parameter then became your domain. So since your domain is negative infinity to positive infinity, then it graphs the entire thing. Okay, so that's all that you need to know for now about parametric equations. Again, just be familiar with what they are, what they look like, how to graph them, then how to convert back and forth from parametric mode to Cartesian, and then also we're going to throw in some polar functions later on.